In second block, there really weren't any questions from the minor summative, I think in part because it was day one and pretty straightforward, kind of some of the techniques we've already seen. But if you did have questions on that, I'm happy to help with that. The only other opening slide I have for you guys is a reminder about your Pythagorean identities in particular. Okay, I think you probably remember the other ones, the quotient identities and all that good stuff, but you want to make sure you have your Pythagorean identities written on your top of your page every day that we do trig proofs, because you're going to have to refer back to them, okay? I only have the first one memorized, and I generate the other two just by dividing through by sine squared theta and cosine squared theta, and I write it at the top of my page. So you'll see, even as we work today, I'll be referencing my paper where I have all three of those written out. Because it's with the ones and pluses and minuses, there's just too many things to think that you're realistically going to remember those without making little careless errors when you're trying to substitute. Okay, so last call. Any questions from the minor summative? Does everybody have the Pythagorean identities written down? If not, remember they're in the Schoology folder as part of the blank and completed notes for this. Let's go ahead and get started on our first example of the day. So let's get to the first chapter. So what do you spy with your algebra eyes? What do you see? What are you thinking? See, what are you thinking? Okay, so one thing I see, first one's supposed to be me, and then second one will be you guys. So Aditi says multiply, and that's what I'm thinking as well. In fact, I'm thinking I don't even have to FOIL it out, because look a little closer at those. Those have the same first term, same last term. One has a plus and one has a minus. Those are the factors of the difference of perfect squares. And I see Alice Pham spotted that. She just went straight to, that's going to be secant squared theta minus tangent squared theta, because those are the factors of the difference of perfect squares, the difference of perfect squares. If you don't see that yet, then go ahead and do FOIL it out or distribute. I like just thinking of it as distributing. Secant times secant is secant squared. Secant times negative tangent theta is negative secant tangent. Tangent theta times secant theta is positive secant tangent. Those cancel each other out, so there's no middle term. Tangent times negative tangent is negative tangent squared theta. Okay, so that's our first step, just multiplying it out. Okay, I also see that we're trying to get it to simplify to 1, so we're looking for everything to go away if it can. And so now that we have squareds, anytime I see squareds, I want to consider my Pythagorean identities. So I go grab my notes with my Pythagorean identities, and I look for the one with secant squared theta in it. And secant squared theta, it's the one that says tangent squared theta plus 1 equals secant squared theta. So when I see secant squared theta in my, so when I have secant squared theta minus tangent squared theta, my first question is, can I get that whole expression matched? Can I get that whole expression matched? And if I look at this, I sure can. If I subtract tangent squared theta from both sides, that's going to give me 1 equals secant squared theta minus tangent squared theta. So I actually can get that whole expression, secant squared theta minus tangent squared theta. That's what that right side equals. So what can I substitute in for it? It equals 1. So I can substitute 1 in for it, and we did it. We did it. Without even realizing we were so close. Without even realizing we were so close. We got it. Okay. Questions for me about that? So when I get squareds, I always consider the Pythagorean identities. Can I manipulate them to equal either the entire expression or part of the expression? And if so, is that helpful to me? Okay, and it was. So you guys try that other side. Go ahead and give that other side a try. It looks like it's also the factors of the difference of perfect squares. Let's see how you do on that. Remember, I really would like more of you guys in the Pear Deck so that I can see your work and help with common mistakes and corrections, give you feedback. Okay, so on that last one, Aditi did it a different way, but she still got there, okay? Good, and that worked as well, Aditi, that worked as well. Good job. Make sure you look to see the way that we did it because it's a little bit more elegant of a technique that will speed you up sometimes. Okay, good. Okay, so a lot of you squared those perfect squares and got cosecant squared theta minus cotangent squared theta. Okay, cosecant times cosecant is cosecant squared. Negative cosecant cotangent, positive cosecant cotangent cancel each other out. And then we get the negative cotangent squared theta. Okay. All right, so then we want to go look for our Pythagorean identities. So let's go look at our Pythagorean identities. Co goes with co in the Pythagorean identities. So cosecant and cotangent are in the same one. They're in the one that says, and I'm going to erase this up here because this is my little scratch work, so I have some room to work here. So the one with cosecant and cotangent is the one that says cotangent squared theta plus 1 equals cosecant squared theta. Okay, can you manipulate that to get it to be the whole expression, cosecant squared theta minus cotangent squared theta? Well, we already have positive cosecant squared theta here on the right. So if we subtract cotangent squared theta from both sides, and again, this is scratch work. Some of you can just do this in your head. Just manipulate those in your head and that's fine. Okay, that's going to be 1 equals cosecant squared theta minus cotangent squared theta. 1 equals cosecant squared theta minus cotangent squared theta. So there we have that expression, cosecant squared theta minus cotangent squared theta. And that's what we currently have in our proof. So what can we substitute in for it? What is it equal to? It's equal to 1. We did it. We did it. Okay. Questions about that? Okay, if I'm going too fast, let me know. Okay, I want you guys to be able to follow what we're doing there. Okay. This idea of manipulating the Pythagorean identities to get them to equal an expression that you can substitute for in your proofs, super important. And so we wanted to start with just a couple of basic practices where we had to do that, where we have to manipulate the expression and substitute. What questions can I answer about that? Okay, let's take it up a notch and let's try something else. Okay, so what do you spy? Oh, that's our same one. Let's see. What do you spy with your algebra eyes? What do you see? What are you thinking when you look at that expression? What do you see? What are you thinking? Okay, well, I can tell you one thing I see is that we've got an exponent of 4 and an exponent of 2, and that the two sides are very similar. They both have a 4th power and a 2nd power, but the trig words are completely different. We've got secant on one side and we have tangent on the other. Okay, so I noticed that. The other thing I noticed is that both terms do have a common factor. Okay, so I'm thinking about factoring, and when we factor, our first step should always be to factor out the common factors. So let's do that. What they both have in common is a secant squared theta. So I'm going to pull out a secant squared theta out of both terms. Okay. What does that leave me in the first term? Remember, factoring it out is like dividing out. So when I want to know what that equals, I can just think of it. Let me erase this here to show. As dividing each term by secant squared theta. and see what that leaves behind. Okay, so in the first term, the secant squared theta on bottom cancels with 2 of the 4, and that leaves me secant squared theta. Minus, in the second term, anything over itself is 1, so it leaves secant squared theta minus 1. Remember, you can always check your factoring by redistributing. Secant squared times secant squared is secant to the 4th. If I erase that and look at my original, okay, that is secant to the 4th. Secant squared times -1 is negative secant squared theta. Okay, so you can always check your factoring by redistributing. Questions on that factoring part? Questions for me there? Thoughts or ideas? Okay, I've got lots of expressions with secant squared, and I want to end up with tangents. So since they're squared now, since they're all squared now, that makes me consider my Pythagorean. So if I go find my Pythagorean identity with secant squared in it, where is it? It's the one that says tangent squared theta plus 1 equals secant squared theta. Okay, so what can I substitute? What can I do? What do you see? What are you thinking? Okay, well, the first thing I see, but maybe I want to erase some of these distributing lines so we can see what's going on here. I'm going to clean that up a little bit, sorry. Okay, so what I see when I take a look at that expression is I see that we already have secant squared theta by itself, and it equals tangent squared theta plus 1. So when I have secant squared theta by itself here, I can substitute in tangent squared theta plus 1. Okay, can you see that on the right side? Secant squared theta equals the left side tangent squared theta plus 1. So for that one term, secant squared theta, I substituted in the 2-term expression tangent squared theta plus 1. Questions on that part? Okay, the next thing I see is that we have the expression secant squared theta minus 1. Can I manipulate this Pythagorean identity? Can I manipulate it to get it to look like secant squared theta minus 1? You betcha. All I have to do is subtract 1 from both sides. And that gives me tangent squared theta equals secant squared theta minus 1. Okay, can you see that? I can get it to equal secant squared theta minus 1. And what does it equal on the other side? Just a tangent squared theta. So where I have secant squared theta minus 1, I'm going to substitute in just tangent squared theta. So with this substitution, we went from 2 terms in pink to just the single expression tangent squared theta. Because we can see by our Pythagorean identities, they are equal to each other, and so we can substitute that in. Questions for me on either one of those substitutions? So far, so good? Remember, good students ask questions. If you're stuck, now's the time to ask. Or if you don't see how we made a jump, now's the time to ask. Okay, so what are we going to do now? So let's take a look at where we're at. Let's see where we're at and where we're headed. Okay, so I want a bunch of tangents. I finally have it to all tangents, so that's feeling pretty good. These are bumped up next to each other, so what does that mean? That means multiply. That means we need to multiply. So I'm going to distribute everything in the first parentheses times everything in the second parentheses. When I distribute the tangent squared times tangent squared, that gives me tangent to the 4th theta. When we multiply like bases, we add exponents. Okay. When I distribute the 1 to tangent squared theta, that's going to give me positive tangent squared theta. Have that plus sign in between there. And comparing to what we need to have, we did it. We did it. Just making the substitution and then doing our algebra to clean it up got us to where we wanted to go. It helped us reach our goal. And like I said, sometimes it sneaks up on you like that. You don't even realize how close you are. Questions for me on that? So you guys know you're not my only pre-cal class, right? So like when you guys are really quiet, it makes me worry about you because I've heard the questions other classes have. And I'm like, I'm sure people in this class have those same questions, but we're not asking them. Okay, so let me know what your questions are. Okay. All right, so you guys try using that similar technique on that next one. Let's go ahead and give that next one a try. Let's see how you do there. If you get stuck or need help starting, let me know. I'm happy to help you get started. Okay. With that first one as a guide, we look for and see we've got a common factor. Okay, so go ahead and pull out the common factor there. Okay, so I'm going to call on one of you guys to kind of talk me through this. And so it's okay if you don't know how to get all the way through. We're just going to let you kind of start and help us. So, Veronica, you want to go ahead and help me with this one? Tell me what you see and what you're thinking.
So, for the left side, you can take out a cosecant squared theta from both terms.
Okay, and what does that leave you?
That leaves you with cosecant squared theta minus 1.
Okay, beautiful. Okay, then what?
I kind of got stuck on this part. I don't know where to go after.
Okay, well, you're doing well so far, so let's stop and see. Okay, we've got a bunch of cosecant squares. Anytime we have our trig word square, we want to consider our Pythagorean identities. So let's go find the Pythagorean identity with cosecant in it. Cosecant squared in it, rather. Okay, so the one with cosecant squared in it is the one that says cotangent squared theta plus 1 equals cosecant squared theta. Okay, so what substitutions can we make with that Pythagorean identity? We start with the plain cosecant squared theta. What is a plain cosecant squared theta equal to, Veronica? What can I substitute in for it?
Cotangent squared theta plus 1.
That's right. Okay, because that's exactly what it's equal to, that expression, so I substituted it. Now, in our second parentheses, our expression is cosecant squared theta minus 1. Can I manipulate that Pythagorean identity to get it to look like cosecant squared theta minus 1?
If you, in the original trig function, if you move the 1 to the other side, then...
Exactly. Okay, so if I subtract 1 from both sides, that gives me cotangent squared theta equals cosecant squared theta minus 1. Okay, so what can I substitute in for cosecant squared theta minus 1?
Cotangent squared theta.
Because that's what it equals. Okay, so it equals cotangent squared theta. Okay, so we just did our Pythagorean substitutions, and the reason we did them is because we're trying to get cotangents, and we currently had cosecants. Okay, so that's the reason we changed it. That was what we were thinking. Okay, all right. Now they're bumped up next to each other, so I'm thinking we probably just need to multiply and clean this up. Can you talk me through that, Veronica?
So, first you would multiply cotangent squared theta with cotangent squared theta, so you'd get cotangent to the 4th theta.
Good, okay.
And then it'd be 1 times cotangent squared theta, which would be just cotangent squared theta.
Right, and don't forget you do need to show that plus sign in between. Okay, there's a plus sign in between, so we're going to keep that plus sign in between. Looks good. And without even knowing it, you did it. You did it. Miss Weaver didn't copy the squared there, but it was squared, so you said it right. Very nice. Good job. Okay, so you were really close. You were on the right track and had the right thinking. Once we remembered to use the Pythagorean theorems, then you did beautifully finishing that up. So thanks, Veronica. Very nice. Okay, questions for either of us on that? Okay, Let's see what else we can get up to. Let's try something else. Okay, so we've got 1 minus cosine squared theta over 1 plus sine theta equals sine theta. What do you spy with your algebra eyes? What do you see? What are you thinking? Look at that. Okay, so one thing I see, one thing I'm thinking, I've got cosine squared on the left and sine, and I only want sines. So I know that I want to be able to get rid of that cosine. I just want sines. The other side is just plain sine. So that cosine squared is squared. And anytime I see the squared, I at least consider my Pythagorean identities. So when I find the Pythagorean identity with cosine squared in it, it's the one that says sine squared theta plus cosine squared theta equals 1. Remember, this is scratch work on the side, okay? And some of you can do it in your head, which is fine. But otherwise, it's not part of your proof. You're just seeing, can I manipulate that Pythagorean identity to get cosine squared theta by itself? And I can. All I've got to do is get rid of the sine squared theta, and I can do that by subtracting sine squared theta from both sides. So that's going to be cosine squared theta equals 1 minus sine squared theta. Okay, so where I have cosine squared theta in my formula, what can I substitute in for it? What is it equal to? Cosine squared theta is equal to 1 minus sine squared theta. So that's going to be the first substitution I make. In that next step, I've got 1 minus, and where I had cosine squared theta, I'm plugging in 1 minus sine squared theta. My denominator is still 1 plus sine theta, and I'm going to leave that right there. So the only change I made in that first step was just substituting in 1 minus sine squared theta for cosine squared theta. Questions on that? Okay, so far so good. Now what do you see and what are you thinking? Now what do you see and what are you thinking? I hope some of you at least can see it already. I hope we've kind of pointed things out like this out enough that maybe you can start to see it. Does anybody recognize what's going on in that numerator? What's going on in that numerator? And look at our denominator, and that should really get those algebra eyes popping, getting you at least thinking about it. That numerator is the difference of perfect squares. Can you see that? That numerator is the difference of perfect squares. If I factor it, it's the square root of the first term, 1 and 1, the square root of the last term, sine theta and sine theta. 1 gets a plus and 1 gets a minus. Okay, it's the difference of perfect squares. Can you see that? Okay, and my denominator already was 1 plus sine theta, and that's why I said that denominator should have at least got you thinking about it. I'm going to put it in parentheses because it looks like one of the factors of the difference of perfect squares. You may not be seeing it yet, but you're going to start to see it. We're going to do difference of perfect squares enough that you start to see those patterns, even with trig words in it, which makes it harder to spot. Okay, I see some of you are cruising away. You're not even waiting for Ms. Weaver to finish talking, which is fine. You're working. You're doing your thing. Okay, was that helpful? Was it helpful to change that? You betcha it was. Because now that 1 plus sine theta on top cancels with the 1 plus sine theta on bottom. We've got 1 minus, and if our denominator is 1, we don't have to write it. It just leaves me that 1 minus sine theta. Now, I almost forgot to put my parentheses around this, which would have been a big mistake. This is 1 minus this entire expression. So we'd have to subtract this entire expression. So that subtraction sign kind of distributes to both terms. We've got to do 1 minus 1 and 1 minus negative sine theta. Minus a negative makes a plus sine theta. Questions on that? We had to subtract that whole expression in parentheses. Originally, it was 1 minus that whole fraction. So we've got to do 1 minus that whole expression that that's simplified down to. Okay? And that was super helpful because the 1 and negative 1 cancel, and I'm just left with sine theta. We did it. We did it. That's what we were trying to prove. Okay. Questions on that algebra? Questions for me on that algebra? Make sure you can follow that, okay? Let me know what questions I can answer. Because you're about to have to do one on your own that's just like it or similar to it, okay? So any questions for me on that algebra? Good students ask questions. All right, I assume that means you're ready. You're ready, you're ready? Let's let you guys try this next one on your own. 1 minus sine squared theta over 1 minus cosine theta equals cosine theta. Very similar to what we were just doing. Oh, it equals negative cosine theta. Let's see if you can do that. Give it a try. I think we did it was very similar. Just a second, Rudy. So we did 1 minus cosine squared with me, and it equals positive sine theta. So now, oh, in the type, yours has extra slides put in, right? And I realized that last block, and so I deleted them out. So yes, you do have them. So so you're Xing out that one, like you just did the X block here, and then you've got more on the other. So these two are duplicates as well. And here we're finally, yeah, oh, they're there. They're there. Yeah, we found that out last block. Sorry about that. Oh, I got it sharing, I think. Hold on. Nope. There we go. Oh. Sorry, guys. I had you on the wrong slide. That's probably what the chat says. Okay, no problem, Jisoo. Thanks for letting me know you're here. You can go ahead and join the Pear Deck. The code is up there in the corner. KWTWMT, KWTWMT, and I'll change your attendance while we're talking about it. Thanks for checking in. Okay, and I'm going to have one of you guys kind of help me talk through what you see and what you're thinking. So let's go ahead and give that a try. Rita, can you help me with this one? What do you see? What are you thinking?
We can use the Pythagorean identities for sine squared theta.
Okay, that's the one that says sine squared theta plus cosine squared theta equals 1. So what substitution are you going to make? What are we going to have what will our first step be?
You can subtract cosine squared theta to the other side.
Okay. Okay, and that'll cancel and give us sine squared theta equals 1 minus cosine squared theta. Is that what you got?
Yeah, and then you can just put that in the numerator.
Okay, so what's it gonna, read me the whole second step. What should it look like?
It would be 1 minus cosine squared theta over 1 minus cosine theta.
Okay, so far so good. She just substituted for that sine squared theta. For that sine squared theta, she substituted the 1 minus cosine squared theta. Looking good. Now what?
Then you can rewrite the numerator as 1 minus cosine theta times 1 plus cosine theta.
Right, those are the factors of the difference of perfect squares. Same first term, same last term. One gets a plus and one gets a minus. Now remember, when you take me to the next step, you still want to read that 1 minus out front, right? Like we're still writing the whole expression. So just read me the whole expression. What about our denominator?
1 minus cosine theta.
Yes. Okay. And now when I get to this point, I like to put the denominator in parentheses because it kind of helps me see what's going on better. What do we do next, Rita?
You can cancel out the 1 minus cosine theta on the numerator and then the denominator.
Excellent, excellent, and good math vocabulary. What does that leave me with?
1 minus 1 plus cosine theta.
And notice that it's still in parentheses, okay? So you do want to still include those parentheses with it, okay? Now, for the next step, you're just going to actually subtract that. And so what do we get when we subtract that, Rita?
So it would be 1 minus 1 minus cosine theta.
Perfect, because she subtracted each thing in the parentheses gets subtracted. Very nice. Okay, and what does that clean up to?
1 minus 1 is just 0, so it'll just be 1 minus negative cosine theta.
Okay, equals negative cosine theta. Very nice. And that's what we wanted. She did it. She did it. Beautifully done, Rita. Very nice. Very nice. Any questions for her on that? Excelente. Okay, let's try the next problem. Okay, so this is going to be the hardest problem that we try, and the next one that you get to do on your own will be the last problem of the day. Your problem will be easier, but using the same techniques that this one does. Okay, and I say your problem will be easier. I have to just tell you a true story here. Okay, so I'm going to show you this, like how I started working it, what I saw, what I was thinking. Last block, when I started my first step, somebody else is like, why don't we just, and they had a different idea. And I will show you their idea, but I'm going to show you at the end because I still want to demonstrate a technique that'll be helpful to you in other problems. And that student's idea, it was Sarah. Sarah's idea was so much faster and easier. I was like, don't. So I'm tempted to show you Sarah's way first. But if I show you Sarah's way first, then you won't get to see this technique that I need you to remember how to do for other problems. Okay, so I'm going to show you more than one way to work with this problem, okay? And just stay with me and try to follow me. Remember, you never need to feel bad if you don't finish it in the easiest way possible. If you prove it, and that's what we're after, okay? So I'm going to show you what I saw and what I was thinking when I looked at this problem. Okay, so I saw we have 1 plus tangent over 1 minus tangent, and we're trying to get to cotangent theta plus 1 and cotangent theta minus 1. Well, the first thing I spied with my algebra eyes, I saw those terms in the numerator and the denominator, and I'm like, those are conjugates of each other. Those are conjugates of each other. So I really wanted to multiply by the conjugate. But then I realized, wait, multiplying by the conjugate won't help me because even if I end up with a tangent squared theta, I can't get from tangent squared theta into cotangents of theta with the Pythagorean identities because tangent and cotangent are not in the same Pythagorean identity, okay? So I'm like, all right, I don't want to do that. But I thought about it, but I don't want to do that. So then I'm like, okay, why don't I just change everything to sine and cosine? So I started by changing everything to sine and cosine. So I did 1 plus sine theta over cosine theta over 1 minus sine theta over cosine theta. Okay. Now, I wanted to simplify that fraction. It's a compound fraction. I wanted to get rid of the denominators. And it is so much faster to use the technique. Hopefully you learned this in Algebra 2, if not sooner, that you can just multiply the entire compound fraction by the common denominator. And so my common denominator here is going to be cosine theta. But what I do to the numerator, I've got to do to the denominator. Okay, so I'm going to multiply by cosine theta over cosine theta to get rid of the denominators, to kind of clean up this fraction, okay? Now, this is only legal because I'm really just multiplying by 1, okay? Now, the fact that I chose that 1 to look like cosine theta over cosine theta, that's the strategy of choosing a well-chosen 1, multiplying by a well-chosen 1, and that's the phrase used in math. And we can choose to multiply by whatever we want to multiply by. As long as we do the same thing to the numerator and denominator, we'll change the appearance, but we won't change the value. So let's do that. I'm going to multiply the entire numerator by cosine theta, and I'm going to multiply the entire denominator by cosine theta. Now, you may be fine with leaving it as looking like cosine theta over cosine theta. Some of you may really prefer to put cosine theta over 1 over cosine theta over 1. It'll help you realize what's in the numerator and what's in the denominator when we're distributing. Okay, so when I did that, cosine theta times 1 was cosine theta. And when I distributed to the second term, the cosine theta on top canceled with the cosine theta on bottom, and that just left me with plus sine theta. Any questions on that in the numerator? Just distributing in the numerator. Everybody okay with that? Because I'm going to do the same thing in the denominator. When I distribute the cosine theta to the 1, I get cosine theta. And when I distribute it to the second term, the cosine theta on top cancels with the cosine theta on bottom, and I'm left with minus sine theta. Okay, so I got there and I'm like, well, that was pretty nice. It cleaned up. It's looking pretty simple. I feel pretty good about how it looks, but it's still nowhere near cotangent theta and 1. When I looked at that, I was like, okay, they still look like conjugates of each other. So I was tempted to multiply by the conjugates again. But I'm like, if I multiply by the conjugates right now, this is going to start to get complicated. And this expression is supposed to stay pretty simple. So I'm like, tangent and cotangent are pretty similar to each other. I thought, what if I went ahead and worked the other side of the expression? Okay, we don't usually like to do that. We like to work one side of the expression only. But I'm like, let me just see what happens if I work that other side of the expression. So I did. I changed the same technique. I changed cotangent to cosine theta over sine theta plus 1. And in the denominator, I changed cotangent theta to cosine theta over sine theta minus 1. And then I wanted to get rid of that common denominator again, so I multiplied both the numerator and the denominator by the common denominator. So what would my common denominator be there? It would be sine theta. So I multiplied by sine theta over sine theta. And put that in parentheses to remind yourself, you've got to multiply the entire numerator and the entire denominator by that. If you want, you can put that over 1, okay, to help you make sure that you do it correctly. When I distribute, the sine theta on top cancels with the sine theta on bottom, and I'm left with cosine theta in the first term. When I distribute the sine theta to the second term, it gives me plus sine theta. When I distribute in the denominator, the sine theta on bottom cancels with the sine theta on top, and I'm left with cosine theta. When I distribute to the second term, -1 times sine theta is just negative sine theta. And when you compare, we did it. We did it. We got the two sides equal to each other. Now, I say we did it, but remember I said this is the first school I've ever been at that they let you just prove the two sides equal to each other. Everywhere I've ever been, for colleges, other high schools, they'll let us work at the second side if we get stuck. That's a legal approach. But usually then once we see how we can get them equal, we have to come and work it backwards from one side to get it all the way to that other side. So I started looking at this and saying, could I make this left side equal that right side? Could I have done it? And if I look at the next step, going backwards, going up this side, what I needed to do was the opposite of multiplying by sine over 1. So what I needed to do was I needed to multiply by 1 over sine theta. I needed to multiply by 1 over sine theta over 1 over sine theta. Because that's the opposite of that's going backwards here. So that's undoing it, multiplying by the reciprocal. So I needed to multiply by 1 over sine theta over 1 over sine theta. And because when I do that, if I distribute that, when I distribute to the first term, that gives me cosine theta over sine theta. When I distribute to the second term, that gives me plus sine theta over sine theta. Over, when I distribute in the denominator, that gives me cosine theta over sine theta. And when I distribute to the second term, that gives me negative sine theta over sine theta. Okay, now, so I saw what the opposite of it would be. I was like, I totally could do that. So that gets me unstuck and I can see it. And I was just wondering to myself, could I have thought of that? Could I have gotten myself unstuck here on my own? Could I have realized what we needed to do? And I could have if I noticed we've got a plain cosine theta and we want it to turn into a cotangent theta. So how does cosine theta compare to cotangent theta? Well, it needed that denominator of sine theta. And that's what we got here when we multiplied by 1 over sine theta. It gave us that denominator of sine theta. And more than that, it was super, super helpful to us. I'm going to erase this right side now since I just used it to get unstuck. Okay, I just used it to get unstuck. So let's erase that so that I can have a little more work room here. Because usually that's what you do. Like all of my college professors, we had to work from one side only. So we could work the other side just to get unstuck, but we still had to come write it from the one side. So now that equals, if I come up here, that equals cosine over sine theta in the numerator, that's cotangent theta. Sine over sine theta simplifies to 1, so that's plus 1. In the denominator, cosine theta over sine theta is cotangent theta. Minus sine theta over sine theta is 1. So that's minus 1. So that gives us what we were looking for. And so there, we did it. We did it. Okay. But using that right side to work backwards to get to the left side. Okay. So when I did that, I was like, okay, I could have seen that. And then when I was looking a little bit longer, I was like, what did I do? Total technique, starting from beginning to end here. I'm like, I multiplied by cosine theta over 1 to get rid of the denominator. And then I multiplied by 1 over sine theta to add what I originally wanted. Okay, and then I realized, well, an even cleaner, prettier proof of this would have been, and this is optional, you don't have to do it, would have been instead of multiplying by cosine theta over 1 and then 1 over sine theta, is if I had originally multiplied by, let's do that, by both, by cosine theta over sine theta. Over cosine theta over sine theta. Okay, so if I had done that originally to my red step here, I could have gotten straight to this last step here because I wanted to go from a 1 to a cotangent and from a sine over cosine to a 1. When I distribute that, cosine theta over sine theta gives me cosine theta over sine theta. Here, the cosine over cosine cancels, the sine over sine cancels, and I get my 1. Okay, same thing in the denominator. When you distribute, that'll give you cosine theta over sine theta, and then the cosines cancel and the sines cancel, and you got the 1 in the denominator. So that would have been even prettier. Okay, so when you get stuck, you can still keep working, and you can kind of figure out techniques, and it can give you ideas of things you can do in the future if you do get stuck. Okay. Now, I know I gave you guys the spoiler alert. I said there was a much faster, cleaner way to work this, okay? But it's important to understand this idea of multiplying by the common denominator to clear the compound fraction, okay? And that's what we did originally. We multiplied by cosine theta over cosine theta to clear the fraction, okay? But now that I've taken you through kind of the pretty intense little exercise in algebra and proofs and kind of thinking backwards, I want to show you what Sarah's beautiful idea was. And some of you may have had the same idea. Okay, so some of you may have had the same idea. So remember, if we're ever working a proof and you've got another way that you want to try, you can always tell me and we'll give it a try. Even if you're not sure if it's going to work, we can give it a try and see if we can get it anywhere that works. So when we started that, I had Sarah put a pin in it and we finished it. But then we came back and tried her way. And I was like, oh, bless. I love it. I love it. Okay. So Sarah said, we've got tangent and we want cotangents and they're reciprocals of each other. So instead of changing to sine and cosine, she's like, why don't we just change to 1 over cotangent? Remember, tangent that's our quotient identities, that tangent and cotangent are reciprocals. So why not just change to 1 over cotangent for tangent in both the numerator and the denominator? So 1 over cotangent theta. Okay, and now we still need to use that technique that I was talking about. We still need to get rid of our denominators. So we're going to multiply both the numerator and the denominator by the common denominator, which would be cotangent theta. So I'm going to multiply by cotangent theta over cotangent theta because that's just 1. So it's legal to do because we're just multiplying by 1. Multiplying by 1 changes its appearance here, but not its value. So that's legal. Okay, so when we distribute, to that entire numerator. Cotangent theta times 1 is cotangent theta. When I distribute to the second term, the cotangent on top cancels with the cotangent on bottom. You can put this over 1 if you need to help you see it, okay? And that just leaves me plus 1 in the numerator. In the denominator, when I distribute, the cotangent theta times 1 gives me cotangent theta. When I distribute to the second term, the cotangent theta on top cancels with the cotangent theta on bottom, and it just leaves me minus 1. And in 2 much shorter steps, she did it. She did it. Okay. I told you there was a prettier way, okay? But you see, even as teachers, we don't always think of the fastest way to get there, but we can get there, right? So you don't want to stress yourself about, oh, is there something I should be doing that's faster? You just want to try it and see if you can get there. The techniques that you'll learn along the way, the things that you'll learn along the way, if you're critical about your thinking and go and re-examine your thinking, will only help you have more tools and more ways to get unstuck as the problems get more and more complicated, okay? Any questions for me on that much more beautiful way that Sarah did that one? Okay, so now it's time for you to use that same technique on a similar problem, only as promised, yours is easier than mine originally was, although Sarah made it look pretty easy with the way she approached it. This is our last problem of the day together, so let's have you guys give this one a try. Go ahead and give this one a try on your own. Let me know if you get stuck or need help. Oh, sorry, Aditi, I just saw your question, and remember to feel free to unmute and get my attention if I don't see your question in the chat sooner. Was that on that last problem? Do you want to, or do you still have that question, or do you understand now? Still need to see it? Okay, let me hop back to it then. So you guys can keep working on that one if you've copied that problem, if you're working on it. In just a second, I'm going to hop back and show her on the previous problem. Okay. So your question, Aditi, was why do we multiply by sine theta and cosine theta? We're trying to clear the fractions in the denominator. That's why. So right now, when I started, it's kind of a mess here to kind of get back to it and see. So let me kind of erase this right side and help you see that. Okay, so I'm just going to kind of write this again in red here so you can see what we have. So we had 1 plus sine theta over cosine theta. And again, that's another reason for you to ask your question to unmute and get my attention, because then it saves us the time of having to recreate where we were at when you had the question. Okay, so you wanted to know why did we multiply by cosine theta over cosine theta here? We did it because we have a compound fraction and we're trying to clean this up. It's not supposed to stay a complicated expression like this. We're supposed to get it to equal this side. So to do that, I knew I had to get rid of this compound fraction. So I multiplied by whatever the common denominator is. So that's a technique called multiplying by the least common denominator. And it saves you the step of first getting the common denominator and then clearing it, because it takes care of it at the same time. If you'd like to, I can show you that longer process of getting the common denominator first and then clearing it, but you'll see it'll do the same thing, okay? And so that's why we distributed it to both terms, okay? All right, so let's go ahead and see how you're doing on this last problem. Got 10 minutes to learning lab time, so I know we'll be finished before then. Let's go ahead and see, get you guys back to this problem. Some of you may have needed me to get the Pear Deck back there so you could start working on it. And when I learned that technique of just multiplying both the numerator and the denominator by the common denominator, I loved it. I was like, holy cow, that saves us multiple steps and lots of time. And it was just a technique I had never been shown in any of my math classes, so I just didn't know it. One of my coworkers at a previous school showed me, and I was like, holy cow, let's do it. Let's go. So I always make sure I show that technique. It really saves you multiple steps. It's looking good. Gia, can you talk us through what you're doing there, ma'am?
I just distribute the cosecant to 1 over sine
Okay.
theta.
Uh-huh.
Then minus 1, I'm all over 1 over sine theta plus 1.
Okay. Because we were trying to get to sines, right? So you just went ahead and changed them to sines. Okay.
Yep. And then multiply like both numerator and denominator by sine theta.
Okay.
And then I got 1 minus sine theta.
Okay, so that was the 1 minus sine theta. Okay.
And then over 1 plus sine theta.
And she did it. She did it. Very nice. Okay, now she understood that multiplying, no problem, and she did it beautifully. If you need to kind of talk it through or explain it, we can explain a little bit more. She was fine with leaving it as sine theta over sine theta. Some people I know do better when they see it as sine theta over 1 over sine theta over 1. Then you see that that sine theta on top cancels with the sine theta on bottom, and that's how we got the plain 1. Sine theta on top, sine theta on bottom gives us the plain 1 for the first term. When you distribute to the second, you just get negative sine theta and sine theta. Any questions about that? Okay, that's all we have for you today. So you guys are ready to go to your Schoology folder and go ahead and start working on your minor summative. Okay, there it is, that little puzzle piece right there. It'll be the same thing as today, where it won't be due until 5